Welcome. I want to present 10 more theorems in graph theory. It's for me also a way to get a little bit organized and stay in shape with technology and everything. I have here, first of all, a theorem which I'm very excited about. Number one deals with a barycentric refinement of graphs. So this can be also formulated, everything can be formulated also with simplicial complexes. But once you when you have a graph, what you can do is you can look at all the complete subgraphs. And this forms a simplicial complex. And when you take two of these simplices and one is contained in the other, you connect them, you get a new graph. And this new graph is called the barycentric refinement of the original graph. Now, it's interesting to see what happens if you are going to refine this again and again and again. So I have an example here of a graph, and you see how it is getting refined again and again and again. And you can especially be interested in the spectral properties. It's a very exciting thing in general to look at the spectra. You can look at the spectra of the Kirchhoff Laplacian. Another Laplacian is the Hodge Laplacian, which is a very nice Laplacian because it also deals with differential forms. So the first one acts on the one forms, two forms, and three forms, etc. So it's important to see that graph theory is a very general framework also for physics. When you are looking at the, for example, you can define the Maxwell equations on this graph here, which we have here, and the magnetic potential is then just a function on the edges, and the electromagnetic field is on the triangle. So this is a two form. And if you are looking at the eigenvalues, it's very important from a quantum mechanical point of view also that you are interested in the spectral properties. And I was interested in the case when you are refining this, what happens with the eigenvalues. And I was a little bit surprised that it really doesn't matter with what graph you start. If you start with a graph, for example, this is a graph which is that has a three-dimensional maximal dimension. So there are tetrahedral, there are K4 subgraphs, but there are no K5 subgraphs. So this is actually a planar graph. You could flatten it. This is also a planar graph. This is a tree, and if you look at trees, this is a one-dimensional graph. It doesn't have any triangles and no loops. So this is these are classes of graphs which we can study. And for example, if you start with this graph and you look at the eigenvalues of the Laplacian and you iterate the refinement process, you end up with a universal density of states. So the spectrum converges in a nice way, like in random matrix theory you have such situations, or random Schrödinger operators you have such situations, or in the central limit theorem you have such a situation where the law of a probability distribution converges to the Gaussian law. But so here we understand in one dimension, we understand completely what happens. So there is a function which a limiting density of states. In two dimensions and more, we can establish that there exists a limit, but we don't understand yet whether there are gaps, for example, in the limiting density of states, whether there are point eigenvalues. It's a very, very exciting topic, very classical topic, also in play from the point of view of statistical mechanics, point of view of solid state physics. And it's very interesting that you actually get in the limit, you get to an almost periodic situation, the variant of the Litsky theorem, which is very useful here, and tells you what happens is if you have, for example, if you have two graphs. And so what happens with the spectrum, what happens if you make out of this tree you make a forest, what happens with the eigenvalues. They don't change a lot, and you can estimate exactly how the spectrum changes under such small perturbations. That was part number one about barycentric refinement, a very, very classical topic in combinatorial topology. Dieudonné once said this is one of the pillars, right? Incidence matrices, which also come here just next. The incidence matrices, barycentric refinement. So and then duality. We talked about duality last time. Poincare duality. These are kind of core principles of of topology, combinatorial topology, algebraic topology, and this is spectral relations are more also from an analytic point of view interesting. And you come to spectral parts also here, for example, with the zeta function, spectral properties come back here also here. Very exciting also about these operators here, which are different from the Kirchhoff Laplacian, but related somehow, and there we have also a very interesting spectral properties. So spectra are something very, very interesting, especially for a physicist who is interested in spectral properties of a geometry. So that was part number one. Part number two, I want to talk about something also which I think is extremely exciting. I'm surprised that nobody is really jumping on it, because it's isospectral deformation. I was motivated, of course, by Witten's isospectral deformation of the exterior derivative, which is a kind of a semi-classical tool which allows you to get from quantum mechanics to classical mechanics by going closer and closer to the critical point. It's a very exciting idea, very powerful idea. And so that impressed me a lot. And I also, in my thesis, worked on isospectral deformations of Jacobi matrices. And these are total lattices, and also in the infinite dimensional situation, you can look at that. Now, here, a couple of years ago, I found this isospectral deformation of the exterior derivative. It doesn't matter whether it's a graph or a Riemann manifold. In a Riemann manifold, you get just pseudo differential operators deformation. But in the continuum, you always have to battle with technical things. So what happens in the case of graphs, finite graphs, is that you have just finite matrices. You can compute this. These are ordinary differential equations. And it's very exciting, because what you see is when you take this isospectral deformation of the exterior derivative, there are many of them. So essentially this is a symmetry within geometry. What happens is, if you look at the D and you deform it and the Laplacian does not change, like actually what happens here, the Laplacian D squared, the Dirac operator squared, which is the Hodge Laplacian, especially the Kirchhoff Laplacian, nothing changes. Anything classically in quantum mechanics, the Schrödinger equation doesn't change, Maxwell equations or gravity, all these equations, Poisson equations, whatever equations which deal with the Laplacian doesn't change at all under this deformation. This is completely invisible. But there is an interesting thing. What happens is that because the D changes, what you have is the D actually becomes smaller and smaller, distances change. So you can interpret this with Kahn's formula as an expansion of space. And so you have, without any input, no deus ex machina or anything, actually you get an inflation at the beginning, which is very, very vexing. So you get initially very, very fast expansion, and then it settles to a constant expansion rate. So that's very, very interesting, and it's an integrable system. So integrable systems are very exciting in mathematics. It's a symmetry of the geometry, and you can ask yourself, why does this happen? So it doesn't actually matter here. You know, if you take this system and you evolve it backwards from the start, it will also expand. So it always expands. Whatever you do, it will always expand. And the Dirac operator will develop a diagonal part, which is kind of interesting, because usually the Dirac, what happens with the exterior derivative, that you have only side diagonal parts. And but still, kind of, if you take D squared, you have this original Laplacian. So nothing is visible from any classical point of view. It's just very, very exciting. But it's just mathematics. Even so, the physics of relations are really vexing. So that was number two. Very exciting topic. Now, number three deals with trees and forests. So this is an example of a tree. A tree is a graph which has no loops, no triangles. In particular, a forest consists of several trees. So this is an example of a forest. And what you are interested in general, if you have a graph like this, how many trees, how many spanning trees are there inside? This is a very classical topic. Cayley has a formula there for the complete graph. Kirchhoff matrix tree theorem tells you that the number of rooted trees are trees where you fix one of the vertices. So that's kind of it's more elegant to look at rooted trees or rooted forests. And the number of rooted trees is the pseudo-determinant of the Kirchhoff matrix. So it's a product of the non-zero eigenvalues of the Kirchhoff matrix. So L has non-negative eigenvalues. So if you take 1 plus L, then you get always positive eigenvalues. So pseudo-determinant of 1 plus L is the identity plus L is the determinant, and there you get the number of rooted trees. That's a theorem. It's called the matrix forest theorem. It's a theorem of Chebotarev and Shamis, who I have displayed here. But it's all a consequence, right? Easy consequence of Cauchy-Binet, of a more general Cauchy-Binet result. So I'm very fortunate to have found a generalization of Cauchy-Binet. This is a very classical topic in matrix theory. So that if you find a new identity about finite matrices, this is really a huge luck. And so what I was able to do is, for example, to get the characteristic polynomial of a product of two matrices in terms of minors. So it generalizes Cauchy-Binet. Z is equal to 1 here, and f, the d0. The d0 is just the analog of the gradient. This is the gradient, and that's the divergence. So the Laplacian is the divergence of the gradient, like in classical, but that's a zero Laplacian on zero forms. And what you have here is you can just immediately, from this formula, you immediately get both the matrix tree theorem and also the matrix forest theorem. So it's a very natural thing. It's also interesting, by the way, to look at the relations between the number of trees and number of forests. I recently looked at that. Might write a little bit more about that in the future. So that's number 3. Very interesting topic. Very classical linear algebra topic. Number 4 is a topic I have worked with Tom Tucker for a while, and it's actually kind of turned out to be almost too easy, but it's a quite interesting relation. There's a Riemann Hub Rights result, which you have a Riemann surface or some topological space, and it's a cover, which means there's a symmetry. So if, for example, in the sphere you have a symmetry mapping the top to the bottom, so it's a reflection symmetry. If you identify things which are in the same orbit of that group, if you identify the top part with the bottom part, what you get is a disk. So the Euler characteristic of this disk is 1. The Euler characteristic of the sphere is 2. So what happened is the Euler characteristic has been divided by 2. So that's actually in general true. The Euler characteristic of the whole space divided by the group order, a number of elements in the group you're factoring through. The Euler characteristic of that quotient is just, kind of you just divide. But there is a connection, a correction part, and the correction part are things where things are branched. So this is also branched because what you have is on the rim here, it's not 2 to 1, but it's 1 to 1. In graph theory, it's actually completely analog to Riemann surfaces. You can take Riemann surfaces like a Bresel here. I have a Bresel here, kind of a Riemann surface with genus 2, and you can look at you can look at symmetries, and so it has all this Riemann Hub Rights formula has been developed in in complex analysis. But for example, you take a graph here, and for this graph you have also a symmetry here, and this symmetry leaves invariant several parts. It leaves invariant these points and edges. Also, this whole triangle is fixed. So you look at that. These are actually things which enter in this ramification part. So this is very much related also to the Brouwer-Lifshitz formula, which we have talked about 2 weeks ago. And it's actually, the proof is essentially just Burnside lemma in each dimension of each part of the k-dimensional part of the simplicity. The key is actually just set theoretical result. You have a group acting on on a set, and you look at the fixed points, you have a Burnside formula. It's quite interesting. For example, let's look at the thing. What I have here, maybe I have to explain a little bit. So if you take C4, for example, that's C4. So this is a natural group action, which is a Z4, which is the cyclic group with 4 elements. So what happens if you actually let the group act on itself, and for the space you let act on itself. So what you end up with only one point, and that single point has then a kind of a loop attached. And when you look at this formula here, what happens is, because there is no fixed point, there is no ramification point, you would actually expect that the Euler characteristic was 0. It would also be the Euler characteristic is 0. But in order to stay in the class of finite simple graphs, I have to look at the second barycentric refinement. If you look at simplicity complexes, you can actually do with the first barycentric refinement. But here we need the second barycentric refinement. And the reason is, if I take now Z4 and act on the second barycentric refinement, so the first barycentric refinement is C8, the second barycentric refinement is C16, and I take the quotient, then I get again a C4, which is again a circle. So I take a circle and identify points which have 90 degrees after 90-degree rotation. What you get is again a circle. This works in general. You can take any group action on a graph, and this formula here gives you the Euler characteristic of the quotient. So we don't here want something like an orbifold or something crazy. We just want, or chain in the discrete, we want to have something which makes sense as a graph. And so that's why I take here the second barycentric refinement. So, but it's a very, very beautiful theme. Also, branch covers are very important in topology. Most spaces you can actually construct as branch covers of simple spaces. That was topic number 4. Now, topic number 5 deals with random graph. So Erdős and Renyi have collaborated for a couple of years. There are nice photos which you find on the web where they were in conferences together with their wives. And by the way, the wife of Renyi was also a mathematician, Catherine Kato, and she was also working with Renyi. But they were working at some point with random graphs. So what you do is you take a number of points, and what you do is you connect with probability p. So it's like a percolation setup. But so you take n points, you take an edge with probability p. So if it is a lattice, this is what one calls percolation. So you are interested in all kind of quantities. What is the probability that it's connected? What is the probability, that you have a triangle there? What is the expected number of triangles, etc., etc. I was mostly interested in the case of the Euler characteristic, but that was still also at the time. By the way, all these things usually you don't even get the referee report when you submit it, because when people look at graphs, they think about one-dimensional simplicity complexes. They don't think about this. For example, here in this case, I'm interested really in the Euler characteristic, which is the number of zero-dimensional vertices minus the number of edges plus the number of triangles minus the number of tetrahedra, etc. So you look at it as a higher dimensional object and not as a one-dimensional simplicity complex, which is a castrated form of a geometry. Also of interest, but completely pales when you compare it with the topology you can do when you look at graphs as grown-up objects with which you can do topology, manifold theory. So what is the expected number of Euler characteristic? I found a formula here which is actually quite simple, because you can find the expected numbers of k-dimensional simply. So I think a referee one pointed out it's trivial. It's trivial, but it's still interesting. And what is interesting, because for example you want to build a graph with, say, Euler characteristic 10 to the 100. And maybe you have 300 or 500 vertices. How do you do that? So I don't know how to do that. It's very, very difficult to construct that. But this result tells you that you actually have such graphs. So it gives you a probabilistic way to prove existence of graphs for which the Euler characteristic grows exponentially with the number of vertices. which is kind of, I mean, the total number of simplices grows exponentially. But the Euler characteristic is an alternating sum. So, in principle, it could be that the Euler characteristic stays always or grows polynomially. So that's very interesting. It's also the dimension. Also here with the dimension, I got a lot of kind of resistance, because the inductive dimension, that's kind of what topologists were looking at, the inductive dimension, the Hausdorff, and in particular, inductive dimension, where you look at the unit spheres or small spheres. What is the dimension of that? And you just take 1 plus the average Euler characteristic of small spheres. So in graph theory, it's a very natural notion. Gives you something which behaves like the Hausdorff dimension in many respects. Behaves like Hausdorff dimension, like also when you take products, and also when you take joins. There is where it's shown that under joins the dimension essentially adds. Of course, for one-dimensional graphs like this, the dimension is 1, because what happens is every unit sphere has dimension 0. So in this case, the dimension is between 2 and 3. So we don't. So I would have to compute it. We'd have to take every unit sphere, compute the dimension of that, and average all these dimensions inductively. But it's an inductive definition. I also computed the expectation of this, which is quite a simple formula. This topic, number 6, deals with something which I found in 2016. All these things which I display here, I had once a proposal for a book. I was asked for making a proposal by a publisher, and then somehow they decided that I'm a Mickey Mouse, and suggested, I mean, they didn't tell it like that, but they suggested that I'm just take somebody else also as a co-author. But somehow I'm glad, because I would have spent some time with writing that text, and I would not have found these energy relations, which is a very interesting thing. So it's actually something which completely let me stop doing anything else. When you look at the graph, what you can do is you can look at all simplices, all complete subgraphs. And now I can build a 0-1 matrix. The number of columns or rows of this matrix is the number of simplices, complete subgraphs. So what you do is you have simplex x and simplex y. Lxy is equal to 1 if they intersect, and 0 else. So that's kind of a little bit more general. I wrote it down here, a little bit more general in terms of stable and unstable manifolds. So the stable manifold is just all the sets which are contained, all the simplices which are contained in a simplex. The Euler characteristic of this homoclinic point, that's Lxy. And in the case when you just take here omega x, that's the kind of classical case. That's kind of the natural energy you take to get the Euler characteristic. Then you get this matrix Lxy, which is equal to, the entries are 1 when they intersect, and 0 else. It's an intersection which is important, so it's not contained in each other, but it's intersect. And then there is an unstable part which is actually related to the inverse of the Laplacian, which is the green function, which is very important in physics. So in physics you are very excited about the green functions, because what happens is the green functions is kind of a propagator. In this case, you have an explicit formula for the green function, and it's finite. The reason is because this matrix here, if the energies are all non-zero, is always invertible. Especially here in the omega x case, it's actually a unimodular matrix. Also, if omega x is equal to, if that hx is equal to 1, you get a unimodular matrix. So it's very, very exciting that you have. And then you think about gxy is the energy between simplex x and simplex y. So this is energies. If you add up all these possible energies, there doesn't have to be an intersection here. All these matrix entries you add up, you get the Euler characteristic of this generalized energy, and the determinant is just a product of these energy values. So in the case of topological case, it's either 1 or minus 1. In the case when hx is equal to 1, it's always 1. And also when the hx, this can be complex, can be quaternion, can be in a C-star algebra, can be very general. What you get is then you get the star, G star is equal to the inverse. So this G is really the inverse. Less than a year ago got this Ising type quadratic part, which is related like the Wu characteristic part, where you just look at all intersecting simplices, and then you take hx, hy. It's kind of like an Ising energy type thing. And then there is also a relation with the square of the green function entries. And this is very, very exciting. It is very exciting that you have Laplacians which are invertible. So there is no singularity. If you look at Laplacians, our Laplacian for space is not invertible, and that's the problem. So you have green functions which have singularities. So the 1 over r potential which you have in gravity or electromagnetism is a singular object. Whether it makes sense or not probably doesn't make sense at all, because what can you say? I mean, infinite energies. I mean, it just doesn't work from a relativistic point of view. Also, so all this physics breaks down in the very small. So it's very exciting. It's somehow that you have this kind of integer. These are actually integer. If these are integers, and so you get integer matrices. It's very exciting. In the case when you have say plus minus 1 valued energies, you get integer matrices. And if the hx is equal to 1, what is very interesting, you get quadratic forms. So the number of positive eigenvalues is just the number of positive energy values. So that's very interesting. So if all the energy values are positive, you get a quadratic form, integer quadratic form. Like interesting in number theory, and the G is isospectral, is the inverse. The inverse matrix is again a quadratic form, and it has the same spectrum. So it's a symplectic property. I'm sure this will have kind of, when we started more. Now, there is an interesting relation between the connection Laplacian and the Kirchhoff Laplacian. It's actually when you look at just the 0 and 1 dimensional, these Laplacian on 0 forms and 1 forms, there's this supersymmetry like McKean-Singer with eigenvalues on the 1 forms is the same thing that non-zero eigenvalues on the 0 forms. So when you look at a graph, or if you look at the graph without triangles, for example, or you look at the graph and you just look at the simplicity complex, ignoring all triangles and higher dimensional parts, then what you get is you get the Hodge Laplacian, which has just 2 blocks. So we have seen here, in this case, these are just d plus 1 blocks if you are in dimension d. So in dimension 1, there are just 2 blocks. There's the 0-dimensional part, the Kirchhoff Laplacian. There's the 1-dimensional part, which is the 1-form Laplacian, which is the electromagnetic potential part. And then you have, what happens is, it's quite interesting that you can actually get the signless Hodge Laplacian, which is just obtained by taking the incidence matrices, and you can kind of take a bosonic thing, you ignore completely the ordering of the things, of the signs. And then what you get is what one calls the signless Laplacian. But what is kind of still interesting is that you can estimate the eigenvalues. You can estimate the eigenvalues in terms of the eigenvalues of this connection Laplacian, which is a 0-1 matrix. And for 0-1 matrix, the matrices you have much more results about, estimating the maximal eigenvalue or the minimal eigenvalue. All kind of results are easier to obtain there. So you have a relation. I call this the hydrogen relation because what happens when you look at the hydrogen atom, so you have the Laplacian, and the Laplacian has a green functions which involve the kernel is the 1 over x minus y absolute value in 3 dimensions. In 1 dimensions, it's the absolute value x minus y. So the force is just discontinuous already. In 2 dimensions, you have the logarithmic potential. In 3 dimensions, you have 1 over r potential, which gives you a 1 over r square force for gravity and electromagnetism. In 4 dimensions, you would have a 1 over r cubed. And so, but these are all singular things. In this case, there is no singular part here. It's just the 1 over r potential, which is kind of what the hydrogen atom is, and explains all the periodic elements which you have. The periodic system of elements is actually just a spectral picture for the Laplacian in 3 dimensions. And so what happens here, that's why, that explains just the name hydrogen relation. But it's quite interesting, and the results, the estimates about the maximal eigenvalue spectral radius is pretty competitive with what other researchers have done, sometimes even better. So it's quite an interesting approach to spectral properties. So that was number 7. Number 8 deals with the zeta function, which is a very exciting topic. It's also spectral theory. So when you have eigenvalues, what you can do is you can look at this sum and introduce a complex parameter. And this really makes only sense if you have positive eigenvalues. On 0, it doesn't make sense for 0. So you usually kind of ignore the 0 eigenvalue part. Which is very nice in the connection part. In the connection part we don't have 0 eigenvalues, so this zeta function is not a hack. Like the Riemann zeta function is already a hack, because you ignore the 0 eigenvalue of the Laplacian. So the Laplacian on a circle has always a 0 eigenvalue, and the eigenvalues of the Dirac operator are just the derivative. It's just by Fourier theory, it's just the integers. And so when the Laplacian has the eigenvalues n squared, and then you take n squared to the minus s. Take the Riemann zeta function evaluated at 2s, you get the spectral zeta function of the circle. So that just can be done for any manifold or compact manifold. You can look at this zeta function. It's usually used for zeta regularization of determinants, which is somehow a pseudo-determinant, because what happens is you just ignore the 0 eigenvalue, which you always have. So that's what you do, you just ignore the 0 eigenvalue part. But so it's quite interesting thing. So for simple finite graphs, so there's a whole book of Terrace. Audrey Terrace has written a beautiful book on if you're interested in the roots. And so here is a proof that the roots converge to s, the real part s equal to 1. It's not very intuitive because the convergence is very, very slow. If you look at the connection Laplacian on the circle, so the connection Laplacian, the nice thing about the connection Laplacian is that things behave better. And what you have in general for a one-dimensional graph, meaning you ignore for a graph, for example, you ignore all triangles, etc. And then you look at the eigenvalues of this Laplacian, which means essentially the eigenvalues of the Kirchhoff Laplacian. But here we are looking at the eigenvalues of the connection Laplacian. There is a functional equation that the function is symmetric. A plus ib is replaced by minus a plus ib. There is an explicit formula, and I don't really kind of understand really there yet what the roots of this function. It's an explicit function. But that's still it's a baby Riemann story, because this is very difficult here. While in this case, when you look at the connection Laplacian, you're essentially in a d-adic integer. So that's about zeta functions. It's a very exciting topic also for experiments. What can you say about the roots of the zeta function? What is the relation between the geometry and the roots? 9 already. It's a very classical topic, because what happens is there's this classical Riemann-Roch story about Riemann surfaces, and you have divisors, and you have the degree of a divisor, and then you have, so classically there's this notion L of D, which then relates with the Euler characteristic. This is the Euler characteristic, or half of the Euler characteristic of the Riemann surface. And then there is a canonical divisor. So you have this beautiful formula, which Baker, Noreen, and others have looked at that in the case of graphs. And the formula is the same. Divisors are just functions on the vertices of a graph. And then you have the Laplacian, which helps you to chip fire. So what you can do is you can take you have an equivalence, linear equivalence between divisors, if they differ by the image of the Laplace. I just bend this a little bit so that the Euler characteristic is actually the Euler characteristic of the graph, in the sense we have kind of always looked at here. So the Euler characteristic is just a full generality Euler characteristic with the number of vertices minus the number of edges plus the number of triangles, etc. So it's a higher dimensional version. But then we have a Laplacian then defined on the graph, on a graph defined by simplices. And so it's done in such a way that the zero-dimensional, the zero Euler characteristic divisors contain the image of the Laplacian. So it's kind of very, very similar. And so you can, for example, look at the zero-dimensional divisors, the space. This is actually a linear space. Some divisors are a way to bring in some algebra. So you can add these divisors, and you have an Euler characteristic of a divisor. And I like to look at divisors also as actually geometric objects. So what you can think about it is kind of you have a graph, and what you can think about it's kind of just in terms of this energy thing. What you have is for every simplex in that graph, you have an energy attached, integer valued energy. So that's your divisor. So what you do is you on the vertices of the Barycentric refinement you have an integer valued function, and these are divisors. And what is very interesting is that you have this notion L of D is just defined in the same way than with Baker-Noreen. So what you want to see, how much can you take away such that it's still linearly equivalent to a positive divisor. And so that L of D is kind of like a distance to the plane where the other characteristic of the divisor is 0. So what this is, and that's kind of the Ki takes 0, and that's another twist. So the K is usually the canonical divisor, which is somehow like a geometric object which represents a divisor which represents the whole space. So what happens here is you can just take your origin not on the level of the geometry, but at 0. So the graph itself is a divisor. So the graph itself is a divisor where you take on vertices the value 1, on the edges the value -1, and so on. And so that's kind of the way to think about it. And then this is actually just a signed distance between the divisor and that plane where the Euler characteristic of the divisor is equal to 0. And that's equal to the Euler characteristic of the divisor. So that's kind of an interesting thing, but it's not so easy because this is not just a distance. It's depends on whether you have special divisors. It's quite difficult to compute this L of D. But I'm interested in this not so much because of the relation between the continuum, but because this Baker-Noreen theory also shows that every divisor is associated to a spanning tree, rooted spanning tree. And so what you can do is because you can add divisors up, is you have algebraic structures on the spanning trees. And so they represent the divisor, and so somehow what you have is the space of 0, the space of divisors with 0 Euler characteristic. That's a linear space divided by the image of this Laplacian here. That's what kind of an analog of the Picard group, which is a finite group. So you can study that, and the order of this group is interesting because it's related to the number of spanning trees, rooted spanning trees, which is actually a huge number. You can compute it using the determinant. That's quite an interesting topic, and it's actually quite also interesting because there are divisors which play a role, which are the Poincaré-Hopf divisors from functions. If you take a function, then you have critical points, and at every critical point you have integer attached. And so what you have is these divisors just have the degree of these divisors. It's just the Euler characteristic by Poincaré-Hopf. So that's used in that theory, and so that's also working here in general when the graph is not considered a one-dimensional object. So there's a lot more here to be done. Also, to see this actually as cohomologically, by looking at the cohomology of that object, of that divisor. And so you can actually see, like in the classical case, one can see as a kind of a Poincaré, Euler-Poincaré formula. And the last thing I want to talk about is an interesting topic. I worked with Frank Uzellis, who is a specialist on Lustanich-Schneermann, and since then I think we were looking at this a little bit in a maybe too complicated way. What you can do is, so when you have a graph, you can ask yourself how many contractible patches do you need to cover the graph. So that's a kind of it depends on whether you take contractible or homotopic to one, or homotopic to one within the space. So I think that's all too complicated. What you really want is contractibility, because the other things is just too hard. And so you take contractibility, but the most important thing is that the theorem works. And the theorem is this Lustanich-Schneermann theory, such that the cup length, which is a cohomological property. So it's it depends on how many cohomology classes can you just multiply maximally to get something non-zero. That is related to the category, which is the minimal number of patches, contractible patches you need to cover the whole space. This inequality you can see pretty easily. And also here what happens is with the category, that's related to the number of critical points you minimally can realize. So for example, if the space is contractible, you can just get a function with one critical point. All the points are not critical points except the minimum, because there the unit sphere of S minus the stable sphere is empty. So 1 minus the other characters of the stable sphere is 1. So you have only one critical point. For spheres, these are characterized as discrete manifolds with minimal number of critical points is 2. So in the case of the sphere, all of these numbers are 2, also of a discrete sphere. So if you take a 2 sphere, or 3 sphere, or 4 sphere, or 5 sphere in the discrete, this is always 2. If you take a torus, what happens in a torus case, if you take a torus, then as on a 2 torus it's 3, on an n torus it's n plus 1. Actually for the projective plane, for example, it's already not true. So the cup length is 1. Here the category is already 3, and also the critical points is 3, if I'm not mistaken. This is this Lustanich-Schneermann theory, which is very exciting, because what is this? This is analytic, this is topological, and this is algebraic. So whenever you have these kind of different things which come together, different parts of mathematics which come together, then it is interesting. You can argue here that it's maybe too easy or too simple to be considered worth, but I think this is just arrogance, and I really like the Mickey Mouse world. Which simple things are things which you can teach, and which are going to survive, or which are developed further. So I'm sure many of these things will be developed much more in combinatorics. Okay, that's it for today.